He's from Intel Corporation, working as a software engineer, and is focusing on optimization of system-level performance in HPC. He has his master's degree in aerospace engineering from Penn State University with a focus on computational aeroacoustics and fluid dynamics. Welcome, James.
Hi, thank you. Thank you for that introduction. And thank you. It's good to see such a participant list staying through all through the days till Friday here. So hopefully my talk will be interesting, and we'll wrap up around noontime. Next slide, please. So a quick outline of my talk today. I will be giving a very brief overview on PSM3. Todd covered that really nicely yesterday, so I'm not going to go into the architectural detail. I'm going to talk a little bit about the performance tuning basics and what we need to do to make sure we get the best performance out of PSM3. I'll show some plots for latency at large scale, 100 plus nodes. Also talk about bandwidth and how we implement different schemes to achieve line rate saturation with UD and RC Q pairs. I'll talk a little bit about multi-rail using more than one Ethernet NIC per node, and show some comparisons of Q-pair footprints, Q-pair and memory footprints for PSM3 relative to Verb's RXM. I'll show a slide with HPC application performance at, again, large scale, up to 100 plus nodes, and then wrap up talking about priority flow control and the importance of getting that set up correctly. Next slide, please. I apologize for the formatting on this slide. Something must have went wrong in the transition. But overall, so the goal of PSM3 is to fit nicely and seamlessly in the libfabric provider space. It is designed and built to utilize Rocky at the moment. The focus is on Intel Ethernet 800 products, but it also works with other networks, as Todd mentioned yesterday. The goal is for it to work seamlessly with other middlewares that take advantage of libfabric, so users don't have to rewrite their applications to take advantage of it, and it just works particularly using MPI, which is what our focus is right now. Next slide, please. So there are some tuning basics that we want to cover before we start trying to run PSM3 in Rocky. Firstly, in the user space, we want to use the latest available PSM library, and there's various ways that you can obtain that. We do have public repos available right now. The Intel MPI team has been working very hard on optimizing for, especially in the area of collectives. So we do recommend using version 2019.10 or newer, but it does also work with older versions that support libfabric. At the system and OS level, we want to make sure that we're using the latest Intel Ethernet drivers and IRDMA drivers. Not so much for performance tuning, but mostly for functional and other features. There is a rendezvous kernel module which is being developed by Intel that allows us to take advantage of kernel RCQ pairs to get the best single thread bandwidth out of the system. And as usual, we want to make sure that Turbo Boost technology is taken advantage of with the Intel processors, and make sure that your OS CPU governor is in performance mode to get the best possible latency out of the system. Lastly, at the bottom for network tuning, having priority flow control enabled is imperative for RDMA performance, especially at large scale. And I'll show an example of that in one of the later slides, and talk about how PFC is very important. At the bottom, I refer to the performance tuning guide, which is available, as well as a whole other suite of documentation that we're providing with the Intel Ethernet Fabric Suite. So check that out for more detail. Next slide, please. So here is a plot of latency at a large scale, and by large scale, we're initially focusing on clusters up to 100 some nodes. We have an internal test cluster called Orion, which is outfitted with Intel Ethernet 810 Columbiaville adapters, as well as a two-tier level of Arista switches with the Intel Tofino switch chip. The key point of this slide and what we're showing here is random order ring latency up to 112 nodes that you see we were able to test on. Is that point-to-point latency is not the only latency that matters in HPC. There's a lot of talk about, who has the lowest point-to-point latency, and trying to optimize for that last nanosecond of latency. But really, where application performance benefits is from low and consistent latency at scale. And what you can see here, running on this HPCC random order ring latency test on 112 nodes with 28 ranks per node. This is just over 3,000 cores. You can see that the latency of PSM3 remains very flat on this Columbiaville Tofino network. So this is a sign that application performance should also scale well. Next slide, please. Shifting to bandwidth, these are two plots of MPI bandwidth, and we are comparing the bandwidth of UD mode, which has the lowest memory footprint because it only requires 1 Q pair per process, alongside of the various other RC modes, which are shown by RDMA mode 1, 2, and 3. And again, I apologize for the formatting on this slide. We'll have to get that fixed for the final publication. What I'm showing on the left-hand side is unidirectional bandwidth. So this is point-to-point bandwidth between two nodes with a single MPI rank. The UD performance is shown in light blue, and you can see that the peak bandwidth achieved with UD is usually right around 3 gigabytes per second, up to that 4 megabyte message size. Shifting to the RCQ pairs, you see we get a nice boost in performance up to the line rate of the 100 gigabit adapter. The maroon line here is the kernel RCQ pair, which requires the RV module that Todd discussed yesterday. And then the green and purple lines are the user space RCQ pair methodologies using UD for other types of communication like control. So you can see all RC modes are able to hit line rate unidirectionally on the left and as well as bidirectionally on the right hand side of the screen. The maroon line here, I have an arrow pointing out. This is the rendezvous transition point where we transition from eager to rendezvous. That threshold is tunable, and I'll show an example of that on the next slide. Next slide, please. So this plot shows bandwidth saturation using RDMA mode 1, which is, again, this kernel RC mode. What I'm showing is unidirectional bandwidth as a function of rank count, and 1, 2, 4, and 8 ranks per node. Essentially what this shows is that we're able to saturate line rate with 2 kilobyte messages with around 8 ranks per node. Increasing ranks per node would help with message rate at the very small messages, which obviously you couldn't tell from the scale of this plot. The key tuning that I was talking about on the previous slide is decreasing the message size at which this transition from eager to rendezvous happens, and there's a nice PSM runtime flag that we can use to adjust that. The default is 64,000 bytes. The results on this slide show, a much smoother curve by lowering that threshold to 8,000 bytes. This tuning may become default in a future release. We're still analyzing the impact to application performance before we make that change. Next slide, please. So this slide shows the multi-rail performance of PSM. So multi-rail can take on various forms. In this context, what we have are two Columbiaville network adapters per server, and we're running with one rank per node. The idea of multi-rail is that you can take a single MPI rank and utilize both NICs for message sizes larger than a tunable threshold. So here what I'm showing is bidirectional bandwidth this time with one rank per node. If we use that single rank and do not enable multi-rail, you can see that we get the nice bandwidth saturation in the dark blue line there for a single NIC. Now, enabling multi-rail forces that MPI rank to stripe the messages across all available RDMA ports or the NUMA local RDMA ports, depending on the way you have it configured. In this case, the threshold is set to 128 kilobytes. So you can see at the 128 kilobyte size there, we start to leverage both NICs and scale very nicely to line rate using both NICs around 50 gigabytes per second there. PSM3 multi-rail map can be more prescriptive about which ports to use. By default, PSM will try to utilize all of the RDMA-enabled ports on the system, but you can specify exactly which ports to use if you have a system that's outfitted with a more complicated RDMA network with multiple adapters. I should mention that messages smaller than this tunable threshold of 128 kilobytes are round robin across the available ports. That in itself may add some overhead due to the UPI if you have your adapters on separate sockets. But for the most part, the overhead is very small and is not noticeable for application performance. Next slide, please. So we'll shift gears and show some Q-pair and memory footprint comparisons of PSM3 versus Verb's RxM. So this is the other Rocky solution with Intel MPI and libfabric using RxM. What I'm showing here is the number of Q-pair comparison on the top plot and the total memory usage on this on the aggregated from all the nodes involved in the job. This is a 64 node run. The benchmark is WRF, the weather researching weather application with the ConUS 2.5 kilometer benchmark. As Todd discussed in the architecture meeting of PSM, especially with UD mode, RDMA mode 0, we have very low Q-pair and memory footprint because of that linear Q-pair scaling dependency of UD. On the x-axis is the sample number, so this is basically a 1 hertz sampling. So you can think of the x-axis as wall clock time. In terms of number of Q-pairs, PSM has significantly less Q-pairs than RxM. And in terms of memory footprint, it's competitive in terms of memory footprint, maybe slightly less memory footprint than RxM. The application finishes, as you can see in this case, in about 50% of the time as the same application running over RxM. I put a little note down there on the lower right. If we were to run the same application with RDMA mode 1, the memory footprint in this configuration is about 495 gigabytes, so it's still similar to the UD mode for this app, and there would be just shy of 10,000 Q-pairs that are activated for the application at the 64 node scale. Next slide, please. So here's a comparison again of application performance of PSM versus Verb's RxM. This is on the same cluster that I shared the random order ring latency scaling with. In this case, so we have those 112 nodes available to us to test on internally. We also have been running tests comparing with EDR InfiniBand, but in the spirit of the technical nature of this conference, we didn't want to show any comparisons. But what I can say is that Ethernet with PSM3 is relatively competitive with EDR up to the 32 node scale that we've tested. What you can see on this slide for a few different applications that we've tested is the scalability of PSM3 is very good compared to Verb's RxM. In some cases, 3 to 5x better than what the performance would be without PSM3. On the upper right, I show a little overlay of what the performance would be with a PSM3 tuning. And this tuning is necessary because, as it turns out, priority flow control was not fully tuned on this cluster. We're still waiting to implement those tunings on this cluster and remeasure performance, but there are some ways that we can improve the performance of applications with PSM flags if PFC is not fully tuned, as I'll discuss on the next slide. Next slide, please. Okay, so for priority flow control, it's well known that PFC is required to get the best performance out of Rocky. It's not always obvious at small scale, so if we run applications at, say, 4, 8, or even 16 nodes, we might not always see the performance deficit without PFC enabled properly. But as we start running applications with very high core count CPUs or at much larger scale, as I showed on the previous slide, it becomes very obvious when Rocky is not enabled appropriately. There are various PFC recipes available. The most common one that we encounter is when you run a data center bridging mode on the switch and you set your NICs up in willing mode so they inherit the settings of the switch. This seems to be the most straightforward and easiest way to enable PFC, and when you add more nodes to the cluster, those nodes automatically adopt the PFC configuration on the cluster. From what we've seen, switch documentation on PFC is not always very clear or complete. And oftentimes, the recipe varies very subtly between switch manufacturers. So the key point here is that PFC configuration must be validated very carefully on your system, especially when you look at performance at higher scale. A symptom that PFC is not configured correctly is that if you pace your senders, and in this case, we can reduce the number of available flow credits to PSM3, that will improve performance. One of the first ways we saw that we had an idea that PFC was not configured correctly or tuned correctly is that we were seeing that by pacing the senders, the performance was actually going up, and that's sort of counterintuitive. There's an environment variable called PSM3 print stats. This is a very lightweight profiling tool that you can use to view various performance metrics of PSM in terms of connection establishment, drops, message types, and this tool will also highlight drops and retries. And by lightweight, I mean you can enable PSM3 print stats, and it's less than 1% impact on application performance, arguably within run-to-run variation. So that's a very powerful tool that I recommend using if you're going to start running with PSM3 if you suspect any type of performance issue. PFC is configured properly if and only if you have no TX or RX drops. Even if you have PFC configured, it's possible that you are exceeding the buffering capability on the switch, or the existing switch settings for headroom and other tunables. And in that case, you're still going to start dropping packets. So it's important that you use tools either on the host, such as ethtool, or the RDMA counters available from the in this case the Intel RDMA driver, or even the switch counters. It's important to make sure that your X on and X off counters are both there for transmit and receive. Oftentimes you may see a host, if you look at the illustration on the bottom right there, what I'm showing here are TX and RX priority pause counters for a NIC. Oftentimes, when you first configure priority flow control, you may see that the TX counters are non-zero, meaning that the host is sending priority pause to the switchboard, but the RX counters are zero. And if the RX counters are zero, especially at larger scale, it essentially means that that switchboard is not communicating the pause packets back to the host. And this is sort of like a 50% implementation of PFC, which can cause a lot of problems. The last point on the bottom is that PFC may need to be tuned. An example of this is the Arista 7170 switches that we have internally. The headroom needs to be increased, in this case at 32 nodes, from about 18 kilobytes to 48 kilobytes. Now, this seems like a relatively small change. Essentially what this means for priority flow control is once you hit the limit and you start, you send a TX pause packet, that switch needs some buffering space to consume all the packets that were already in flight. And if that headroom is exceeded, then it's going to discard those packets anyway, even though it already sent a TX pause. So in the one internal study that we've done, it was very important to increase this headroom, and we are developing recipes to share with customers on how to do that on Tofino-based switches. Next slide, please. So wrapping up, PSM is a new libfabric provider that we've shown allows for very scalable application performance. Two-node micro benchmarks are not indicative of application performance. Although Ethernet has some clear penalties in terms of point-to-point latency, what we see is that the latency remains flat at large scale, and in turn, application performance is pretty competitive with other technologies. Latency, memory, and queue pair accounts scale well with PSM3, and proper configuration of PFC is very important for Rocky performance. Next steps, we're going to be looking at exploring applications that benefit from RDMA mode 1. We showed, in this talk, we showed very good improvements in point-to-point bandwidth using these RCQ pairs. But mostly we've run applications with RDMA mode 0 right now because the applications just don't demand that high bandwidth that we're looking at. We're going to be focusing more in the AI realm of applications, which should benefit from that high single thread bandwidth. We're going to expand the range of application testing, as I mentioned, really trying to utilize the PSM3 performance metrics that I talked about to help us tune applications and close gaps on competition. And we're also in the process of developing PFC recommendations for much larger clusters as the one that I shared today. So that's all for my talk. Thank you very much. And I see there's a couple questions here that I can...
Right. I can read for you if you like.
Sure.
Was it a single Tofino system used under test 32 ports where you tuning PFC?
Yes, that's a great question. So our initial observations with PFC were on a single Tofino switch where all 32 nodes were connected to the same switch. And that is the configuration where we had to increase the headroom size. Now what we need to do is take that recipe and that study that we performed and extend it to the larger two-tier network up to that 100+ node level that I was showing.
Okay, thank you. And then for 64 hosts, I would assume at least 4 switches were used.
Yes, that's correct. The two-tier network that I mentioned, it's definitely it's actually a fabric capable of supporting up to 512 hosts, and we were only using a subset of those hosts in the application performance tests.
Okay. That's all the questions I have today. Any other questions for our speaker? Okay, I guess not. Thank you, James.
Thank you
for your
very
time
much.
here.
Thank you.
Hey, one comment actually, Vladimir went on and made a comment. We need to share the recipes for Broadcom, Mellanox, and Intel. So I see. So I guess he's making a comment.
Yeah, that's a good point. We are testing on various types of switching internally, and yeah, we need to make sure that the PFC recipe is behaving well across all those switches.
Okay, cool. All right, thank you, James. See you next year. I mean, you can hang on here for the workshop, but we'll see you speak next year, is what I meant.
Thank you.